everyone, and welcome to my lab. Are you ready to learn? Yeah! Are you ready to have some fun? Yeah! Well, let's get started then. In my lab, whenever we do experiments, we obey all the safety rules. I want everyone to notice that I have my goggles on, and I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution, and it is really ready to be used, just like that. I'm going to put it right here where you and I know where it is in case it is needed. Now, when you came in, you noticed that we have a lot of different chemicals on the tabletop, and we also have some up in the air. What do we have up in the air? Balloons. How many balloons are there? 6. And what color are these balloons? Red. Mumble, mumble, mumble. That's what I heard you say, right? I love that sound because everyone is free to express their observations any way they choose to. I can ask you a question and get the same answer from out of you. How many balloons are there? 6. And what color are these balloons? Red. There's that mumble, mumble again. Yeah, there are actually 2 green ones, 2 yellow ones, and 2 red. Oh, what do you suppose we have in those balloons? Helium. Now you say helium. Some of you say helium because you know from experience that helium-filled balloons are lighter than air. What we're going to do is find out what's in these balloons by using this torch and this flame. And I will tell you that helium is a gas that doesn't burn. So what I'm going to do is bring the flame close to the balloon, and then we'll see what happens. I notice some of you are covering your ears. Why are you covering your ears? Because you know from experience that there might be some sound energy. All right, here we go. Experience, that's a key word. We learn things not only to store them in our memory banks, but to use them. So here we go with the first one. You ready for this? So that balloon had in it the gas helium. What we always do in science is repeat the experiment. So we're going to do the experiment once more with the second green balloon, and here we go. Did the same thing happen? Exactly the same thing happen? All right, so those 2 balloons had in them the gas helium. Now we move over to the balloon that has, what color is this balloon? Yellow. Let's find out what's in this balloon here by putting the flame to it. Now I ask you, did that balloon have helium in it? No. That balloon had in it a gas we call hydrogen. And hydrogen combined with oxygen in the air in an explosive reaction. And what do we always do in science? Let's do this experiment one more time, but let's do it with the lights out, please. All the lights are down, please, all the way out. Ready for this? Here we go. You sure you're ready? All right. Did you see that ball of fire? Yes. Did you see it better with the lights on or the lights out? That's something we keep in mind whenever we do experiments that release energy in the form of light. We do them indoors and we do them in the dark so we can watch them better. Right now, I want you to watch that very last explosion in slow motion. So look at the monitor. You'll see the flame. There it is. There's that big orange reddish ball of fire. So we've got 2 more balloons. We've got a whole bunch of other experiments. What should I do next? More balloons? More balloons? All right. You noticed that when I was doing the experiments, as we moved from the green balloons to the yellow balloons, the sound energy was getting louder, right? So, because you and I obey the safety rules, what I want to ask each one of you is to protect your ears from potential damage by taking both fingers and stick them in your ear like this, okay? I can't do that and do the experiment, so I'm going to use this to protect my ears. If you can hear the sound of my voice, that means you don't have your ears well protected. I see you smiling, that means you heard the sound of my voice. Please protect your ears very, very carefully as we move now and try to ignite this balloon. That balloon had in it a mixture of hydrogen and oxygen. The air has about 20% oxygen, but we put more oxygen inside that balloon. What do we always do in science? Repeat the experiment, and we do it safely, right? So here we go. And let's do this one in the dark, please. Let's have a quick look at the last explosion in slow motion. Watch the monitor. You won't hear a sound. Oh, that was really, really fast, wasn't it? That's again because we had more oxygen inside the balloon than what is in the air, which is about 20%. So we do all these experiments, we do them safely, and we've had now some explosions, right? And these are examples of what we call uncontrolled combustion reactions. This is a controlled combustion reaction. This is a controlled combustion reaction right here. But explosions, we call them uncontrolled combustion reactions, and we want to do them very, very safely so no one gets hurt, and we all enjoy the bright light that we see and the high sound that we hear even with our ears protected. So what I'm going to do next is take my bucket of dry ice and move over here where I have a dishpan, and it's empty except for air. Air is also invisible and has no odor, right? And I have some boiling water. You can see it right here. I use the gloves now to protect my hands from heat. And so what I'm going to do is take the water, hot water, pour it in here. What do you see coming off the top? Steam is invisible. You cannot see steam. Water vapor is invisible. Look, this room is full of water vapor. Otherwise, my throat would be drier than it is right now. What we're seeing is condensed water vapor. We're seeing a mist. And when the water vapor that's condensed hits the air and gets to the same temperature, it dissipates. All right, so I'm going to put this right over here and turn the heater down. Then I'm going to take a bucket of dry ice and put all the dry ice in here. I'm still here. This is how they make fog in the movies sometimes. They take boiling water and add dry ice to it and then blow it. You notice once again that the fog is moving, telling us that carbon dioxide gas is heavier or denser than air. Now, I want to do another experiment. This experiment I want to do with this candle. I want to reach into my back pocket, and I want to pull my wallet out. What do people usually keep in their wallets? Money. What else? Credit cards, pictures, what else? Driver's license if you're old enough to have one, right? So I want you to pay close attention, as you've been doing. Pay close attention to these experiments because I don't want anyone to miss out on anything that's really exciting. So here we go. I take one $20 bill out of my wallet and I put it in the flame just like that, and it disappears into thin air. Did you see that? I wish I had a camera to get the expression on your face over there. You know that was not a real $20 bill. That was a fake dollar bill, a $20 bill. That was a phony $20 bill. It's called flash paper. What do we always do in science? Repeat the experiment. So I take what looks like a $20 bill, but it isn't. All right? And now you pay close attention as I bring it close to the flame here and see what happens. It didn't even touch the flame. You saw that, right? Right? So did you like that experiment? Yeah. Good, good. All right. Thank you. All right, so now what I'm going to do is reach into my wallet and get out a real $20 bill, okay? There's nothing phony about this. Yes, oh, wow, she said. I heard that. I saw you say that. Okay, $20. You know what I'm going to do with it, right? Yeah. The same experiment. I'll do the same experiment, but I want you to see that I have a jar here, and I have a liquid in this jar. What do you suppose this liquid is? Well, what does it look like? What does it look like? It looks like water. You know from experience what water looks like. So what I'm going to do is take the $20 bill. I'm going to soak it in this clear and colorless liquid. That's how we really describe this. Water is a clear and colorless liquid. And I'm going to try to fish it out. Try to fish it out. Here, make sure it's soaked well. Fish it out. You see it's dripping like any wet object would. Now, you ready for this? Take a close look at the $20 bill. It may be the last time you see it in this form right here. And I put it in the flame. And there is a $20 bill on fire, or is it? You saw the flame, didn't you? But the $20 is intact. So now I ask you, can this liquid be water? No. You know from experience that water doesn't burn under these conditions. I'll tell you what this liquid is. It's a mixture of water and something we call rubbing alcohol, isopropyl alcohol. Half and half, 50%. We also added a little bit of table salt to it so that we can see the color of the flame better. The yellow color that we saw was because of the table salt that's in there. Otherwise, as you know from experience, the color of the alcohol flame is bluish. Well, this is a good $20 bill. It's a little bit wet, but I'm going to put it back in my wallet because I'm going to put it to good use later on. So I put this one back here, put my wallet back in place. Did you like that experiment? Yeah. Thank you. And now I'm going to, for the next experiment, I want you to see this book. This is a very colorful book. It's chemical demonstrations, and I wrote this book. You see my name is right down here, right? You see that, right? Right? So I want to open the book and just very quickly read the instructions for the next experiment. So bear with me as I do that, okay? Here, ooh. This is no ordinary book. This is a hot book. Actually, it's not a book at all. It's just the book covers. On the inside, there are two batteries. There is a filament from a light bulb, and there's a wick. I put some lighter fluid on the wick and soaked it before you came to my lab. There's one other thing I want to show you. At the bottom of this book, there is what looks like a small button. What color is it? Red. Right, red. Okay, so now I open the book and move it away from my face. Safety is paramount. When I push the button, the chemical energy that's stored in the batteries changes into electrical energy, and the filament lights up. Just like all filaments, all electric filaments of this type, when they light up, they give off electricity and they give off heat. And the heat ignites the fluid that I soaked the wick in. So you remember the fire triangle? You need three things to have a fire, right? You need something that burns, you need oxygen from the air, and then you need a source of ignition, usually heat, okay? So here we go. I move it away from my face, push the button, there, it comes on. Okay, now you tell me what happens when I close the book. What happened when I close the book? Just tell me out loud. No more oxygen. You know what? You're like the students in my class. they give a correct answer, but not to the question that I asked. The question, oh, you recognize that, huh? The question that I asked is, what happened when I closed the book? What happened when I closed the book? The fire went out. Why did the fire go out? Because there was no more oxygen, all right? All right, so I opened the book now. Is there oxygen or not? Yes. Yeah, but there's no fire. How come? We need 3 things to have a fire. What should I do? Just stop talking and push the button, right? That's what I should do, okay? But first, I move it away from my face, right? I push the button, there it is. We teach about the fire triangle, so we learn how to put out fires, not to start fires. All right? You like that experiment? Yeah. All right. Hello, Hina. Hinano, are you a student at the university?
Yes, I'm a student at University of Wisconsin, and I am studying music and business, and I also do science experiments.
Oh, you like science experiments. But,
I do.
But I see that you have your flute with you. Would you please play something more for us?
Sure. Could you get my music stand?
Of course.
I will be playing an arrangement of the Carmen.
Bravo! Bravo, Hinano. That was fabulous. That was really beautiful.
Thank you.
And now you said you'd like to do some experiments.
I do. I can show you some.
Right now?
Yeah, sure.
All right. Shall I follow you?
I have my safety goggles on and my gloves on.
All right. Very good.
So I have 6 solutions with me here. This blue solution is copper sulfate. I'm going to mix it with hydrochloric acid, and let's see what happens. This green solution is nickel sulfate. Let's mix it with dimethylglyoxime.
Very nice.
Not all solutions have to be colored solutions to create a colored solutions. This colorless solution is lead nitrate, and this colorless solution is potassium iodide.
That's beautiful, Hinano. That's not only beautiful, but very colorful.
Yes, and color can be also referred to in music with sound and tones. To help me show you this, I would like to invite Professor Mark Fink to join us.
Thank you, Hina. It's my pleasure to be here with you today. Normally, I play the oboe, a woodwind instrument, but today what I have with me is the oboe's big brother, the English horn. And the tone is produced with a reed, two pieces of wood that vibrate against each other to produce a sound. My reed isn't feeling too well today. Usually it sounds better when I put the reed on top of the instrument. You're a great audience. Hina, would you like to play something together to demonstrate
Sure.
our different colors of our instruments?
Let's play a duet, an excerpt from the William Tell Overture by Rossini.
Ladies and gentlemen, Hinano Ishii and Professor Mark Fink. Thank you very much. Thank you. Now we go to this part of the lab where I'm going to do an experiment with dry ice. Dry ice is solid carbon dioxide. I'm going to put my gloves on to protect my hands from frostbite. I'm going to take chunks of dry ice and put them in this conical flask. We call it an Erlenmeyer flask. And this dry ice will sublime inside the flask and outside the flask. But I want to fill the flask with as much carbon dioxide as I can in this short period of time. And what you see there is a little mist, right? That's the condensed water vapor. There was a little moisture inside the flask. So there it is. And I now will move over and light the candles that we have over here. You help me out. How many candles do we have? 1, 2, 3, 4, all right, 6 lit candles. And what I'm going to do now is take the flask, the Erlenmeyer flask, with the dry ice at the bottom, that is undergoing sublimation. And I'm going to lift it up. I'm going to pour the carbon dioxide gas out of the flask. Our carbon dioxide is denser than air. It flowed down. Now I will go back to this side and light the lowest candle on the steps, and then use another gas that is denser than air. This gas is propane. It's in this propane bottle right here. It's connected to a funnel and some Tygon tubing to the valve of the propane tank. So what I'm going to do is fill this beaker with propane gas. Propane is colorless, so we can't see it. So I'm going to do this by opening the valve, and you'll hear the sound of the gas flowing. Here we go. You hear it? And now watch what will happen when I take this beaker full of propane gas and pour the propane gas down the... Do you like this experiment? Yeah. Shall I do it again? Yeah. All right, I'll do it again. We'll put this candle out. I was trying to light up all the candles, but I succeeded in lighting up one. And we want to make sure everything is out of here, right? Including the carbon dioxide gas that formed, right? So it's all coming out. And then I go back and fill the beaker with propane gas. Here we go. And let's try this one in the dark. Let's take a look in slow motion at this very last experiment, all right? And there you see the flame. Merry Christmas, everyone! Oh-ho! Throw like a mighty often! Feliz Navidad! Yes, the well! Merry Christmas! Good Yule! Lovely Yule! Oh, Merry Christmas! Hello, Santa.
So good to be back.
I'm happy to see you here, Santa. Did you get my list?
That big long thing?
Oh, wasn't all that long. I've been good. Haven't I been good? Yeah. Did I get anything, Santa?
We've just got a couple of things now. The rest will be delivered a little later.
Oh, okay. Promises, Santa. But I trust you.
I've got to see if I can find... Oh, here. Yeah, this is one that you asked for.
Oh, yes. Oh, that is the right one that I wanted. Yes, thank you,
I thought there was oh, there's one more.
One more.
Where is it? Oh, here it is. It's very special.
A nice small box.
Little box.
Can I open it now?
Yes, please.
Okay.
Is that what you wanted?
Yes, yes. I see this one small plastic bottle with a colored liquid in it.
Yeah.
All right. And then let me see the other one here. And yes, this is the other one. It's clear and colorless liquid.
Yes.
And I wanted these liquids. You know why I want liquids? Because I want to do some experiments with them.
Could I do with it?
Of course. But you have to obey the safety rules, Santa.
I brought them with me.
You brought them with you, okay. All right. Let's go and do the experiments.
Let's do it. Let's do it.
All right. We have 2 dishes here. And they're empty except for air. And what I'll do is take the clear and colorless liquid and put it right there.
What does it say on the side?
It says it's labeled Li for lithium, so it has in it a compound of the element lithium.
Oh, in the periodic table.
Yes, so your elves are very, very smart. I know that, Santa.
Well, we look at
SciFund.org.
You
You visit there often, I'm glad. And this says copper on it, so this has a compound of copper, of the element copper.
But that's not colorless.
That's not colorless. That's kind of, it's kind of murky green. Is
Right,
what it is.
okay.
Okay. Now, to do the experiment, you said you want to do the experiment. How,
Yep.
What do you
Well,
need? What do you
knowing
need?
what have always heard about your laboratory,
Yes.
we should have some flames.
We
Can
have
we
lots
use
of
that burner?
We can use this burner. This one here?
Yes, that one.
Whoa.
I like this one.
All right. All right.
See, if I push this button.
You push the button.
Ah.
All right. What are you going to do now?
Well, these liquids, this
Yeah.
one has what?
Lithium, copper.
Okay, let's see what happens if we burn the lithium.
All right. I see something there.
You do?
Yeah.
What do you see?
I see a slight color here. What about the
Okay.
next one?
Oh, this one here.
Yeah.
Aha, look at that.
You know what, Santa? Maybe we can see the colors better with the lights off. So can we turn the lights down?
Merry Christmas! Oh, this reminds me of home.
This is just fabulous, Santa.
It reminds me of home, the Aurora Borealis. Isn't that beautiful? Red. Now, this is the lithium red.
That's the lithium compound red, and the copper compound, it gives us the green color.
Oh, that's
So
beautiful.
Yes,
Merry
thank you.
Christmas.
Thank you, Santa. Can we have the lights up here? So,
Oh, wow.
you like that?
That was fun.
So, let's cover them up here.
Okay.
Just cover them up like that. All right. Now,
Hey, that's-
so now, Santa, I promised you and I promised the audience that we will do an experiment with this gift that you brought
Yes.
me. So let me get out what I need here. And this is a sparkler.
You wanted a
I
sparkler?
wanted a sparkler. You and the elves prepared these sparklers
Yep.
for me. And I'm going to do an experiment with this sparkler. This experiment has to do with chemicals that I put in this, in the two, can you hold this,
Yes, I
Santa?
will.
I put the chemicals inside two flower pots. There is iron oxide and aluminum metal. So it's a mixture of rust, iron oxide, and aluminum. And what I want to do, Santa, is ignite this mixture. Actually, what I want to do is put this one over here and go to that box that's over there.
Oh.
Because that's where I want to do the experiment. And what I need from you is a source of ignition.
Okay.
So if you, once again, give me a chance to get this sparkler going. So you ready?
Yeah, I'm ready.
Okay.
Whoa.
All right. So now step back. And with the lights down, please.
My goodness. Oh, my. Oh, my. Merry Christmas again.
Whoa! Santa, this reaction gave off so much heat, it melted the iron that was formed. It was not red hot, it was white hot. Let me show you here, Santa. It's still coming down here. I want to be careful about it. Let me reach in and use the tongs to pick up the iron from the sand where we collected it.
Oh, my goodness.
And there you see. It's
molten
still
iron.
It is, yes. It came. Oh, there it is. Still molten
Oh,
right there.
wow. Molten iron
So-
from all that rust.
Yes, Santa, this is actually a very important chemical reaction, and it's done very safely. You know where it's used, Santa? It's
Where?
used in welding railroads, railroad tracks. Railroad
Oh,
tracks
wow.
are welded by using this thermite reaction. And Santa, you and the elves and the entire audience should know that this thermite reaction is responsible of how the West was won a long time ago when the railroad tracks stretched out to the western part of the United States.
Oh, my goodness.
Yes.
Well, we learned so much, but I have to go. We're double parked out on the
Double parked. I don't want
I don't
to
want
get
another ticket.
No, no. Thank you so
Merry
much, Santa.
Christmas.
Thank you, and the
Merry
same to you
Christmas.
and to the elves. Thank you very much, Santa. Happy
Well,
holidays
look
to
at
you.
Inox then. Feliz Navidad. Merry Christmas, everybody. Merry Christmas, everybody. Gladly Yule. Good Yule. Rudolph, wait for me.
All right, let's take a look at that thermite reaction in slow motion. Just watch the monitor, please. you see the molten iron dropping, that white, and then a lot of smoke. And we have it all contained inside that box that's connected to an exhaust vent so we don't fill the lab with smoke. Now I want to reach down here and get a magnetic stirrer. It has a light on it, so I'm going to turn the light. And I'm going to put on it a large beaker. This beaker is empty except for air, and this beaker has a volume of 4 liters. If you look at it right now, you just learned how big 4 liters is, and you cannot unlearn it. You may forget it. That's different. You think about that. I take a Teflon-coated magnet and put it in there and turn the switch on. And I'm going to use this to mix 3 clear and colorless liquids in the 4-liter beaker. Here are 2 of them, and here is the 3rd one. So I need to speed up this a little bit. I take the first liquid, and I put it in. It's clear and colorless. But as soon as I put it in, you can see it's a little cloudy right now. And then I take the second one, add the second one. Anything interesting happened so far? Yes. Well, the volume increased, right? That's very common. And if I increase the speed, you can see what looks like a tornado. I hope this is the only tornado you will see up close. I take the 3rd liquid, and I add the 3rd liquid. And we see a color change and another color change. Oh, what? I don't see anything happening. How come I don't see anything happening? I'm not looking. What's the big deal about looking? The last time I looked at the beaker, the color of the liquid in the beaker was deep blue. Shall I look right now? I don't want to trip over anything, see? Every time I look at it, it's blue. You tell me when to look, all right? Tell me when to look. Shall I look right now? Right now? You sure? I don't want to trip over anything. Maybe you can help me better on this side here. Tell me when to look, all right? Shall I look right now? Yeah. Right this second. You sure? I don't want to trip over it. Right now? Every time I look, it's blue. What's going on here? I don't get it. I don't get it. Oh, wow. What is it that you were doing that I was not doing? You were looking all the time. I was looking all the time, but not over here. I was looking everywhere else. I was looking at you. When we do experiments, we have to pay attention. We have to be focused. We have to be learning from the different transformations that are taking place. This is an example of what we call a chemical oscillating reaction. It's one of about 50 known such reactions, but this one is very special to me. It's special for 2 reasons. One, it was discovered by 2 high school teachers, and it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. In 1973, they published a paper describing this beautiful, captivating behavior. A second reason it's special to me is that it took researchers, high-powered researchers, members of the National Academy of Sciences. It took them 9 years to figure out what's going on in here. So when we do scientific experiments, we pay attention, we're vigilant, and we try to understand what's going on. We always keep our patience. This has in it about 8 or 9 different chemicals: water, hydrogen peroxide, potassium iodate, malonic acid, sulfuric acid. It has potato starch. The yellow color is the color of iodine. Combines with the potato starch, it turns this deep blue, almost black color. This, ladies and gentlemen, is the Briggs-Rauscher oscillating chemical reaction. At this time, I would like you to welcome my longtime collaborator and friend, Dr. Rodney Schreiner. Rod?
Hello, Bassam.
Hello, Rodney.
It's a pleasure to be here on this 44th presentation, annual presentation. That's quite a record, isn't it?
I'm very proud of that, yes. Thank you, thank you.
You know, what we chemists like to do with anniversaries is to celebrate them using the element whose number corresponds to the anniversary. So we're today featuring element number 44.
Yes, element number 44, ruthenium.
Element ruthenium.
That's the name of it.
Yes. And ruthenium is, like most elements, a metal. And like most metals, it's silvery gray in color. Looks kind of like iron and nickel and platinum. In fact, it's somewhat related to platinum. But rather than showing you an uninteresting gray lump of metal, I went and talked to a chemistry professor here in our department who works with ruthenium. His name is John Barry, and he gave me a bunch of ruthenium compounds, which I have here in this rack, solutions of those compounds. And you can see that ruthenium is a very colorful element. All sorts of colors, almost a whole rainbow of colors.
Very beautiful colors, yes. I like colors, you know that. And I like color changes, too.
Yes, well, speaking of color changes, I'd like to show you one that involves another metal, not ruthenium,
yes,
but vanadium.
All right.
So I'll set these aside and get my solution. Here's my solution of another metal, which is vanadium. And, you know, I was telling you about gray metals. Well, here I'll show you a gray metal. Here's another gray metal. It's zinc. Now, this is zinc metal. This is a compound of vanadium. All of the vanadium atoms in this solution have had 5 electrons removed from them. Don't worry about it if you're not a chemist. You don't need to know what that means exactly. But if we start adding electrons back to these vanadium atoms, something will happen to them. So first I'm going to pour some of this yellow solution into that beaker, and then I'm going to mix the rest of it with the zinc, and the zinc is going to start putting electrons into the vanadium, and we'll see what happens.
So electrons transfer from the zinc to the vanadium.
Right.
One at a time? Or what?
Sort of, well, let's see what happens. Already a color change has happened.
Right.
And that happened because the vanadium atom, each one, got 1 electron. So we went from missing 5 to missing 4. And if we mix it a little more, the zinc will transfer some more electrons. And now we've got missing 3.
That's very pretty, Rod.
And maybe if I stir it some more, we can get it to go to 4.
I see more color change.
It's changing. You know, one of the virtues that chemistry teaches you is patience. Sometimes you need to wait for the good things to happen. And it looks like it's still happening here.
Oh, that's pretty also.
Yes, it keeps going. I think, yes, this is looking familiar.
Yes.
And there.
Beautiful display of color, Rodney. Thank you.
Isn't that pretty? Isn't that pretty?
Right.
Thank you. Well, I've been working with another metal. This is actually a metal. It's iron. I have an iron pipe. And you know you can make sounds with metals. One of them, you can make it simply by tapping the metal. Some musical instruments are made of pieces of metal. Or you can make sounds by blowing air through a piece of metal. Some musical instruments are made that way too.
Okay.
Okay, it's not beautiful. But there's another way I can move air through this tube. If I put hot air at the bottom, the hot air is less dense than the cold air, and it will rise through the tube, so I don't actually have to blow it through. So what I'm going to ask you to do is help me get some really hot air here. There we go, and we're going to put it in the bottom of the tube. And you can hear sort of a noise, but the torch is making a lot of noise, so what I'm going to do is I'll take it away. Cool. And while I was doing this in the lab, I discovered something. Did you know you can pour sound? Let me show you. Here's a cup, my pipe. Let's make some more sound. Okay, I think. You can't see the sound. There it is. That's what happens when you can't see it. I ran out. I must be spilling it all over the place. I suppose you want to know how that works.
Yeah, I would like to know, and they would like to know how it works, yes.
There's something about this pipe that I didn't tell you earlier, in that at one end there is a small metal screen, a very coarse metal screen. Let's see if I can aim it there. Maybe you can see it inside. There's a coarse screen. When I hold that over the flame, the screen gets really hot. When I take it away from the flame, that hot screen heats the air. The hot air rises, drawing cold air through the bottom, and the cold air goes through the screen, and it whistles through that screen as it goes, and it starts to reverberate in the pipe. And when the screen cools off, then it stops making noise. Let me demonstrate again.
All right.
Of course you want to see it again, right? Now it requires the hot air to rise through the pipe. If I turn the pipe horizontal, it doesn't rise. It can't get through. But if I return it to vertical, then it can rise through again. This has nothing to do with it.
Thank you very much, Fred. Now I'd like to do an experiment with small plastic bottles. Here's one. Here's another one. Here's a bigger one. And an even bigger one. I'd like to tell you about these bottles because what they have in them are screws that are inserted, but they're not touching on the outside, on the inside. They're separated by a distance about ½ a centimeter. They're not touching at all. And there's a cork on top of each one, and there's also a clear and colorless liquid at the bottom of each of these 4 bottles. So what I'm going to do is use what is called a Tesla coil, which is a way by which we can generate a spark. If I push the button, there's a spark coming off here, but I want to show you this spark by taking this metallic object and hanging onto it real tight as we turn the lights down, and you'll see how the spark now jumps across. You see it? All right. All right, now with the lights back up, please. What I'm going to do is touch one of the screws in each of the bottles and see if I can make the spark jump across the gap that separates the 2 screws, and we'll see what happens. You ready? Here we go. Let's try this one. What we're doing here, we're setting off an explosion. That's because the liquid at the bottom is actually an alcohol, and the vapor of the alcohol gets ignited when the spark jumps across the gap that separates the 2 screws. Ooh. How about we try this one in the dark? Should we try this one in the dark? Let's see what happens. You ready? You sure you're ready for this one? All right, here we go. Yes, safety comes first, right? So we obey the safety rules. At this time, I would like you to welcome our chemistry lecture demonstrator, Mr. Jim Maynard. Jim? Hi, Jim.
Hi.
What do you have for us?
I have a demo for you that involves this syringe and this small Erlenmeyer flask with a clear and colorless substance in. And I actually have one more thing I need. Okay, so this is my demo.
This looks like a long glass tube.
Yes, it is. It's a long glass tube, and you can notice it's stoppered on both ends. And inside is a clear and colorless gas. It's actually nitrous oxide, also called laughing gas.
Laughing gas. All right.
Okay. We're going to do an experiment with the laughing gas. We're going to combine it with this clear and colorless liquid, which is actually called carbon disulfide. It's a foul-smelling liquid like most sulfides, and it has a structure like carbon dioxide. We're going to take this liquid, we're going to put it in here, we're going to mix them together, and we're going to do a combustion reaction. So in order to do this, though, I need to get up on the table. And I need my syringe. So I'm going to take and withdraw some of this carbon disulfide with the syringe so I don't have to smell it, and because it isn't really good for you. But don't worry, it doesn't hurt a bit. All right. So I'm withdrawing a certain amount of fluid from here, and I'm going to introduce it to this large glass tube. Okay. And in it goes. And I'm going to mix it in a rather special way as well. So, let's take it off here. Okay. 1, 2, 2.5. Okay, I think we're sufficiently mixed. Now, what I'm going to do is light this. So, Bassam, if you could help me find a torch.
Oh, yeah. Here it is.
And with the lights down, please. 1, 2, 3. Thank you.
Wow. Now, what's this yellow stuff on the inside of the tube?
Yeah, this yellow stuff on the inside of the tube is sulfur. So this reaction starts out with the carbon disulfide and the nitrous oxide, and you get nitrogen, carbon dioxide, and sulfur. I like this demo for 2 reasons. 1, it's very spectacular. And 2, Le Chatelier himself, of Le Chatelier's principle, used to do this very demo in front of his students over a century ago. Thank you very much.
Fabulous. Thank you very much. Thank you. Now I'd like to ask you to focus your attention. Yes, thank you, Jim. On this experiment that I'm going to do using colorful liquids. Here is a green liquid, here's an orange liquid, and I have a blue liquid. And I also have a small beaker with a little bit of a yellowish, lightly yellowish liquid. And what I'm going to do is we now express to you my thanks and all the thanks from the people in my lab for your being such a wonderful audience. Here's our grand finale for you. Here's one. And here's another one. And here is the third one. Thank you all very much. Thank you. Thank you. And no matter what you do, remember, always remember, science is fun. Thank you all very much. Thank you again.
Discover holiday fun in the lab of Shakhashiri.
Are you ready to learn?
Amazing experiments. Exciting guests.
Do you like that?
Once upon a Christmas Cheery in the lab of Shakhashiri.
Thank you. Hello, everyone.
Discover holiday fun in the lab of Shakhashiri.
Are you ready to learn? Welcome to my lab.
Amazing experiments. Exciting guests.
Santa knows science, doesn't he?
UW chemistry professor Bassam Shakhashiri explores science that's exciting.
You like that?
Once upon a Christmas Cheery in the lab of Shakhashiri.